So our job now is to see if this kinematic equation for the position for a damped oscillator, if this is a solution to this differential equation. So we have x, so we can plug in for x this expression here, but we also need to know the first derivative of the position with respect to time and the second derivative of the position with respect to time if we are going to test if this is in fact a solution to this differential equation. So the next step is going to be to calculate those derivatives. So I'm going to start with the first derivative of the position with respect to time. Okay, and we have two terms here. We have the exponential term, which depends on t, and the cosine term, which depends on t. So we're going to need to use the product rule, which is the first times the first term, which is a times e to the minus bt over 2m, times the derivative of the second. So we're going to end up with a minus omega sine of omega t plus phi 0, plus the second, which is cosine omega t plus phi 0 times the derivative of the first. So we're going to end up with a, and then we end up with a minus b over 2m out in front, times our exponential e to the minus bt over 2m. All right, so let's just consolidate our terms a little bit. Both terms in this sum have an a e to the minus bt over 2m, so we can pull that out in front. And we have both of these terms now are multiplied times that. We need to multiply the cosine by this minus b over 2m. So the first term is minus omega sine of omega t plus the initial phase phi 0 minus b over 2m times the cosine of omega t plus phi 0. So this is our first derivative with respect to time, which we need to plug into our equation of motion. Next up, we need to take the second derivative. So we're going to take the derivative of this with respect to time again. The derivative of the second derivative of x with respect to time is going to be the derivative of this whole guy. Once again, we have two terms multiplied together which both depend on t, so we're going to need to use the product rule. So we're going to do the first term, which is a e to the minus bt over 2m, times the derivative of the second. We have two of them here. So the sine goes to a cosine, and we get another omega out in front. So we get minus omega squared cosine of omega t plus phi 0. The cosine goes to a minus sine, and we get another omega out in front. So we're going to get plus b times omega over 2m times the sine of omega t plus phi 0. Okay, now we need plus the derivative of the first, which is going to be a times minus b over 2m times e to the minus bt over 2m times the second, which is just this term that we have here, which is minus omega sine of omega t minus b over omega t plus phi minus b over 2m, it's this term over here, right here, b over 2m times the cosine of omega t plus phi. Whew, getting there. So now we have some more terms that we can collect. So I'm going to pull out an a e to the minus bt over 2m from both of these terms, and I'm going to multiply this second term through by minus b over 2m. So we get the second derivative of x with respect to time is equal to a e to the minus bt over 2m. Okay, we have two terms involving cosine. So we have a minus omega squared, and we also have, if we multiply this b over 2m through, we're going to have b squared over 4m squared minus omega squared, all times the cosine of omega t plus phi 0. Now we need to do the sine terms. So we have this sine term here and this sine term here, so that's going to be plus b omega over 2m, and we multiply this through, and we end up with another plus b omega over 2m times the sine of omega t plus phi 0. So rewriting this guy, we get the second derivative of x with respect to time is equal to a e to the minus bt over 2m times b squared over 4m squared minus omega squared times the cosine of omega t plus phi 0 plus b omega over m times the sine of omega t plus phi 0. All right, we're getting there. So now we've calculated the first derivative, we've calculated the second derivative. What's next is to plug that in to our equation of motion. So our equation of motion says we need to take the second derivative with respect to time plus b over m times the first derivative plus k over m times our original kinematic equation for x. All right, so let's do it. We're going to start off with the second derivative. I'll rewrite the equation here. We have the second derivative with respect to time plus b over m times the first derivative with respect to time plus k over m times x is equal to 0. So the first derivative with respect to time, we have a e to the minus bt divided by 2m times b squared over 4m squared minus omega squared cosine of omega t plus phi 0 plus b omega over m times the sine of omega t plus phi 0. Okay, now we're going to have plus b over m times this first derivative, which is up here. So we're going to have I'm going to multiply through by b over m as I go, but out in front we're going to have a e to the minus bt over 2m times, we're multiplying through by b over m, so we're going to have minus omega b over m times the sine of omega t plus phi 0 minus b squared over 2m squared times the cosine of omega t plus phi 0. There's the second term. The last one is plus k over m times x. So up last we have a e to the minus bt over 2m times k divided by m times the cosine of omega t plus phi 0. And that all needs to be equal to 0. All right, so now we have taken our solution for x, we have plugged it into the differential equation. All that's left is a little bit of algebra. So let's start with the sine terms. We have this sine term, and we have this sine term. And we'll also note that we have this exponential term in front of all three terms in our sum. So we can divide both sides by a e to the minus bt over 2m. We have 0 on the right-hand side, so these three guys go away. All right, so with the sine terms then, we're going to have b omega over m times sine omega t right here, and then we have minus b omega over m times sine omega t down here. So the sine terms, they actually cancel. We're going to have plus, now the cosine terms. We have this cosine term, this cosine term, and this cosine term. So three cosine terms. Starting off, we have b squared over 4m squared minus omega squared times the cosine. Next up, we have minus b squared over 2m squared. And last up we have plus k over m, all times cosine of omega t plus phi 0. This has to be equal to 0. All right, so first of all, the cosine is never, there's no way to set cosine of anything always equal to 0, right? We have this time in here, so we can't kill this term. But we can make this term be expressly 0. First of all, we need to consolidate. We have b squared over 4m squared minus b squared over 2m squared. So that's going to give us a minus b squared over 4m squared. And we have minus omega squared. That needs to be equal, or excuse me, minus omega squared plus k over m. Has to be equal to 0. And omega is what we're looking for here, so we're going to get that omega is equal to the square root of k over m minus b squared over 4m squared. And this is exactly equation 14.56. So we have shown that this equation 14.55 is a solution to the differential equation right here. This is equation 14.54 if and only if omega is equal to the square root of k over m minus b squared over 4m, which is the condition of equation 14.56. So we've done the dynamics. We have taken the solution for exponential decay with an oscillation. We have plugged it into the equation of motion, and we have verified that this equation does satisfy the equation of motion if omega is equal to this term here.